Hello, good evening, everyone. I will be taking the introductory part and the beginning section of this project, talking about green hydrogen from hydrokinetic and renewable energy sources. As we know, hydrogen holds potential as an alternative source of energy to reduce greenhouse emissions. But as it stands, fossil fuel is still dominating the production of hydrogen because it is relatively cheaper compared to producing hydrogen from other renewable energy sources. So we are saying that extensive studies and research should be done into looking at how to reduce the cost of producing hydrogen, and that is what this research project is aiming to achieve. First of all, as a recap, why do we look at AEM technology among the main technologies of producing hydrogen? AEM combines the cons of the other technologies and amplifies the pros of these technologies. So it's less corrosive and it is not sensitive to impurities compared when you look at the PEM and the AWE electrolysis. So in summary, this project objective is looking at we're going to explore methods that will aim to reduce the cost of producing hydrogen. Then we're going to look at the pitch analysis approach for optimizing green hydrogen production process. We are also going to look at suitable and cost-effective methods for storing hydrogen and distributing hydrogen. So the two strategies we'll be employing will be running the electrolyzer as a discontinuous process and also reducing or downsizing the thickness of the electrolyzer membrane. Running the AEM electrolyzer as a discontinuous process, here we are going to be taking advantage of the times when electricity is cheaper and when it is relatively more expensive. Electricity, as we know, cannot be stored. It can be regarded as an inelastic commodity. So the prices are always, there are times when it's going to be expensive and when it's going to be cheaper. So from the graph we see in this report, we see that the working day price throughout the 24-hour time frame is more expensive than the weekend price. To carry out effective analysis in a discontinuous process, we are going to be modeling our electrolyzer with the sustained ion electrolyzer that runs under 31.5 bar, and the total power required to run this electrolyzer is about 20 kilowatts. We see that here the minimum, we are going to consider either of these modes where the load runs at 100% of the available power, or during transient period where the electrolyzer is going to run on about 60% of the load for 10 minutes, and then thirdly where it is going to run for running at a minimum load of 20% of the available power. Further in the analysis, we need to understand the concept known as the levelized cost of production, which is generally referred to as the ratio between the total annualized cost of electricity that is produced from our renewable energy sources to the quantity of hydrogen that is actually produced. This ratio is expressed in dollar per kilogram. We have an expression here given in this slide. So, and we have a model here where the plant capital cost is about 900 kilo euros per megawatt. The plant life is about 30 years. The plant construction is for 2 years, and the discount rate is for 8%. From the results, we can see that the cost of production is at a minimum when the operations of the electrolyzer is not working, or in other words, when the electrolyzer is not working. Then we also see that the electrolyzer is most efficient when it runs at low load for most part of the time, or in a case of 1 year, for most of the year. The production rate of hydrogen is found with this analysis to be 4% more than when the electrolyzer is run continuously. And we also see that the minimum cost of electricity to be expended is about $56 per megawatt hour, which produces about $3.27 per kilogram of hydrogen. The other option we look at in reducing the cost of producing hydrogen is reducing the membrane thickness of the electrolyzer. We see that there is a relationship between the thickness of the membrane with that of the movement of hydroxide ions in the electrolyzer. We know that it is this hydroxide ions that is oxidized in order to release hydrogen in the electrolyzer. We see that the thicker the membrane of this electrolyzer, the easier the movement of ions is to the cathode, and in turn which requires minimum amount of electricity or energy. So on that note, we see that the current membrane thickness of most anion exchange electrolyzer, even though it's not commercial, is about 460 centimeters. And from studies, we see that the efficiency of this electrolyzer will increase from 55% to 75% if this thickness is reduced to about 50 centimeters. Thank you. So I'll hand over to my colleague David to give an in-depth analysis of the AEM electrolyzer, as well as throw more light on the pinch analysis. Thank you.
Hello, my name is David, and as my partner has rightly said, we will be dealing with the anion exchange membrane of electrolysis. For our work, we decided to go with two different brands of anion exchange membranes to analyze their performances. The reason for doing this was because this technology is still in the ARA research and development phase. There's still room for improvement. So we decided to take the two best we could find and analyze them side by side. Now, the name of the first one we went for was the Sustain Ion AEM membrane, and the second was the Fumatech AEM membrane. Now, both electrolyzers were simulated to perform at their optimum conditions, which was generally under 35 bar of pressure. 1 molar, the electrolyzer was made up of a 1 molar solution of potassium hydroxide stream, and for the Sustain Ion AEM membrane, its optimal temperature was 70 degrees Celsius, while that of the Fumatech was 60 degrees Celsius. Now, for the process feed streams, for the seawater, the selected process feed stream mass flow rate was about 1 ton of fresh seawater per hour into the system at atmospheric temperature and pressure. For the potassium hydroxide feed stream, we went with about 4 kilomole per hour of flow rate. The reason for doing this, we selected it in such a way that the resultant electrolyte would consist of a 1 molar solution of KOH stream, which was aligned with the optimal performances of both Sustain Ion and Fumatech membranes. Here we can see the process flow diagram for the entire electrolytic process. We start with an input of seawater coming at about 1 ton per hour. It goes into the reverse osmosis section, which separates excess salts from the water. The deionized water goes in here, purified water rather goes in here, and it's mixed with a K-ray stream as well as a recycle stream from down the line of the system. Now the mixture out here, the mixture is done in such a way that the process feed coming in would constitute of a 1 molar solution of KOH. That is, which is then preheated and pumped to add to the optimal pressures and temperature, optimal conditions of the electrolyzer. For sustain ion, we heated it up to the process feed stream up to 60 degrees Celsius and just under 35 bar of pressure. Here it goes into the electrolyzer. From the electrolyzer stack, its separation occurs, electrolysis occurs, and hydrogen and oxygen gas is vaporized. It evolved out of the electrolyzer, while excess liquid, which has been unreacted, is sent to the bottoms. Now, for the processed gas, it goes further into a column separator and separated into hydrogen gas and oxygen gas. The hydrogen gas is then compressed and pumped and prepared for storage. Now, the bottoms product it consists of a mixture of water, excess water, and oxygen gas is then mixed and separated again. And here, oxygen gas, the pure oxygen gas is separated from the water. The water is sent back to the recycle stream and mixed again, and that is where the recycle stream and worked on again, which is where the recycle stream comes from. For the Fumatech process flow system, the process is basically the same, with the major difference being the feed temperature. Optimal feed temperature is 70 degrees Celsius, and the stack conditions the conversion efficiency is a little different. Besides that, all other components of the system work in a similar fashion as the sustain ion system. Now, from our simulation, we were able to evolve about 9.8 kilograms of hydrogen gas per hour using the sustain ion system, and 8.9 kilograms per hour of hydrogen gas using the Fumatech system. There's marginal difference between them. Now, for the power consumed, the sustain ion system electrolyzer system consumed more energy than the Fumatech system, and also produced more greenhouse gases, almost 3 times as much greenhouse gases as the Fumatech system did. So we ran a pinch analysis on both processes with the sustain ion and the Fumatech systems. Now, from the pinch analysis, we could tell that we can observe that the total utilities used in both cases could be optimized a little further, and thereby increasing the overall efficiency of our systems. The sustain ion system used significantly more energy than the Fumatech system, and this same trend is similar with the carbon production, the carbon emissions. The sustain ion system produces almost 3 times as much greenhouse gases as the Fumatech systems. Now, that being said, in both cases, there is significant improvement in the Fumatech system compared to the sustain ion system.